También.
porque yo no sé si... Ok, ¿vamos?
Okay,
Oh,
so today we have a talk about the article that received the best paper prize of Revista de la Unión Matemática Argentina. This is a yearly prize, and it is given, I mean, the winner is selected among all the articles published in our journal in the previous 2 years. So in 2024, the paper that was selected by the jury, integrated by Alicia Dickenstein from Universidad de Buenos Aires, Marco Salvai from Universidad de Córdoba, Demetrio Stojanoff from Universidad de La Plata, and Sheldy, Ombrosi, and myself from Universidad Nacional del Sur. We selected the paper whose authors are François Dumas and François Martin. They are from the University of Clermont-Auvergne. And the title of the paper is Invariants of Formal Pseudodifferential Operator Algebras and Modular Form. In this very nice paper, what they do is more or less the following. When you are dealing with deformations, you need to study brackets, and it has been shown that brackets on modular forms are in connection with non-commutative product in some algebras of invariant operators. So the main goal of the authors in this nice article was to obtain such connection in a formal algebraic setting. So congratulations, you both, on this award, and thank you very much for your contribution to our show. So now it's your time.
muchas gracias. Antes de comenzar, nosotros gustaría agradecer sinceramente a la UMA para distinguir nuestro artículo. Nos sentimos honrados con este premio y será un motivo más para dar a conocer su revista a nuestros colegas en Francia y a invitarlos a publicar allí, a enviar allí sus trabajos. Como dices, estamos también particularmente contentos porque es un artículo que tiene un carácter algo interdisciplinario dentro de las matemáticas fundamentales, entre álgebra no conmutativa y teoría de números. Y es parte de una colaboración en varios artículos que todavía continuamos hoy con François. Entonces, nuevamente, gracias a todas y todos. Y nada, vamos a comenzar la charla en inglés. So, the title is on the first memo. And as you said, oh, uh, this is an interface. This is a paper which is an interface between non-commutative algebra and number theory. And it has its origin in an important paper by Paula Cohen, Manin et Zagier in 1997. This is a very fundamental paper, a Greek paper, which contains many ideas, many original results, and many open tracks. And one of these tracks was on our interest, which is a construction of a linear isomorphism between a space M, which is a vector space of sequences of modular form associated with some subgroup of SL2, and a non-commutative algebra of pseudodifferential operator and the invariance under the action of gamma. Explain a little more. We have here a space, a vector space of which is sequences of modular forms, so which is associated with the action of some subgroup of gamma. And in this paper, they construct a map, a linear map, with some algebra of pseudodifferential operators, and the action of this group gamma on the pseudodifferential operators give rise to an invariant algebra, and this is this map. And here we have an uncommutative algebra, here we have a vector space, and then by transfer of structure, the the space of modular forms is equipped with a non-commutative product. And this non-commutative product is closely related with another very important notion on modular form, which are the Rankin brackets. This is the general frame of this study. A little more specifically, we start with a subgroup of SL2, subgroup gamma, which acts by homography on a C-algebra array of functions in one variable, complex variable Z. There are some analytic assumptions, but I don't explain this point here. This action is by homography. That means that we have the action of gamma on R, which is defined by the action of the AZ plus B over CZ plus D for an element ABCD in gamma. This is the case of weight 0 of a family of more general actions, which are actions of weight K on R, which is defined by this definition. That means the action of weight K of an element gamma of the group on a function f is defined by the homographic action of f multiplied by CZ plus D power minus k. This gives rise to the notion of modular forms. A modular forms is a modular form is a function f such that a modular form of weight k is a function f which is invariant for this action of weight k. This is the first point of view. But what is proven in the paper, original paper, is that the action of gamma on R can be extended by automorphisms on the algebra of pseudodifferential operators with coefficient in R. Psi DOR, this is the first description. This is the analytic description of these operators. In the next slide, we'll see algebraic more formal and more easy definition for us. And the author constructs this linear automorphism between some space, which is the space denoted here by even. Even is very important, which is a space of sequence of modular forms. And then by transport of structure, as explained previously, they obtain a non-commutative product of this space. What are the problems studied in our work? First is to observe that this particular construction is in fact a particular case of a formal general construction for the action of any group gamma acting by automorphism of any commutative algebra R, provided with a derivation. And our goal was to determine conditions, firstly, for the action to be extended, the action on R to be extendable to the non-commutative algebra of formal pseudodifferential operators. This is this algebra denoted in the presentation by B. I will explain a more precise denotation. And then a second step for the invariant algebra, B gamma, the algebra of elements of B which are invariants by the extended action, to be an algebra of pseudodifferential operators, but with coefficient in R gamma. This question was not studied in the original paper. And this description B now leads to the question we have a description of the invariant operators as pseudodifferential operators, and then is to deduce explicit results on modular forms. In the second part of the talk, François will explain precisely the arithmetical result that we can obtain in this way. And the, the other aspect of the paper was to generalize all the formal construction of 1 and 2 in order to include in the study the modular form, which is not of even weight, which was the case in the classical situation, but with modular forms of any weight, even or odd, which is an original part of our study today. Okay. So some words on the general algebraic object to know what is for in non-commutative algebra a formal pseudodifferential operator algebra. We consider R a commutative C algebra. R is commutative. Equipped with derivation D. D derivation means simply that D is linear and satisfies the Leibniz rule, formal derivation. And then we construct the algebra B, which is denoted by an algebra of Laurent series in the variable x, and the D is here to twist the product. I explain. The element of B are Laurent series. That means a classical Laurent series in one variable x with coefficient in R. Coefficient written in the left. Because, of course, the product will be non-commutative. Laurent series, that means that there are only finite numbers of non-zero coefficients for negative index. That means the Fi are all 0 for I lower than the valuation of S. This is the classical object of the Laurent series commutative. The linear structure is the usual, some linear structure valuation, but which is which is particular, is that the product is twisted by the derivation D. That means we have here this relation, which is a commutation law, and which allow to express the product of the indeterminate x on the right by a coefficient, by a series with the coefficient on the left. This relation is sufficient to describe all the products in the algebra, because if we have here from this relation we deduce the expression of the power of k, and then by distributivity and positivity we obtain the product of any series. Just an observation, an easy calculation that I cannot produce here, show that this relation is equivalent to another one which concerns the inverse of the x. Of course, they are Laurent series, so x minus 1 is an element, which is, of course, much more easy, and allows to see that the polynomial in x minus 1 are a subalgebra of B. So we have our object B. This is a very classical, very ordinary object in non-commutative algebra. But there are less classical or non-classical quadratic variants of this construction. We start with our commutative C algebra with a derivation denoted here by delta and not D, and we define this algebra C, which are Laurent series in the variable y. The index 2 means that in this case, the multiplication is twisted by another commutation law, which is this relation. You observe that there are only odd powers of I. The explicit formulation can be written here. And which is not very trivial is that this commutation law ensures to the product to be associative. All the problem is here. So this recommendation is effectively sufficient to define a non-commutative multiplication. And from this identity, by iteration, we obtain this one. That means that this commutation relation concerning y give rise to this commutation relation concerning y square. And this is just ordinary pseudo-differential operator ring in the variable I square, twisted by the derivation 2 delta. So, if we rephrase this construction in terms of extension, we can see the algebra B. Do you see the formula, the last formula in your screen? Yes, okay. The algebra B, can be considered as a subalgebra of the algebra C in the formal variable x power alpha. Voilà, sorry. So they are the two objects. Now, concretely, our questions. We have the group gamma, which acts on R. R is the algebra commutative of coefficients. We can consider the invariant subalgebra. First question, can we give necessary and sufficient condition for the action of gamma on R to be extended to an action on B, the pseudo-differential operator invariance? Second question, the same for an action on C, which is much more complicated. C with a relation between B and C that we explained previously. And if these conditions are satisfied, so we have an action of gamma on B and on C, can we describe the invariant operators in B gamma or C gamma as pseudo-differential or quadratic pseudo-differential operators with coefficient in R gamma? That means, can we write B gamma as an algebra of pseudo-differential operators with coefficient in R gamma? For some x prime, of course, related to x, and some derivation d prime, of course, related to d prime. And the same for. And last question, in this case, is C gamma an extension of B gamma? These are very formal questions and very general. Yes, we have this kind of result. This is the formal part, the formal algebraic part of our work. The action of gamma by automorphism on R extends to B if and only if we have a compatibility relation, that is, that there exists one cocycle P from gamma to UR. UR is the group of invertible elements of the algebra R, such that we have this relation. That means if and only if D is an eigenvector for the conjugation action on the group gamma on the space of derivation. So for B, we have a necessary and sufficient condition for the action to be extendable. Second question, can we describe the extension? Yes. In this case, the extension of the action to B is defined from an explicit relation which gives the action of gamma on the variable x, the indeterminate x, as a series in x with coefficient in R. Of course, we have here the image of the one cosical by the power of the derivation d. This relation, one more time, is sufficient to describe the action of gamma on any element of B. This canonical extension corresponding to this formula is not the only possible, but we know how to describe all possible extended actions. They are much more technical to express, and so for this talk, I only present this canonical form. And if there exists, third question, if there exists B gamma an element X prime whose inverse is of the form is linear of degree 1 in X minus 1, then effectively we can describe the algebra of invariant B gamma as pseudo-differential operators with coefficient in R gamma. So in the case of B, we have complete answer to the question studied here. For C, the first problem is comparable. That is, the action of gamma on R extend to C, which are the quadratic pseudo-differential operators, if and lawfully if we have a quadratically compatibility. That means this kind of relations. So this is the same that in the previous case, but for a particular condition that the cosical, the one cosical P can be expressed as the square of a one cosical. And we can prove for C similar results as those given above for B, but in this case, the formulation is very technical. We have, of course, explicitly definitions and formula in our paper, but I cannot explain here. Just a remark, a comment. The formal pseudo-differential operator algebras are well-known object, very classical object in non-commutative algebra. But that is not really the case for the algebra denoted here by C, this quadratically twisted compatibility. But in fact, there are this algebra C with this particular twist are in fact just a particular case of a much more general construction which appear in the ITs for the description of the discrete variation ring in non-commutative, which are the name lower series on higher derivation. There is also literature on this subject, and this is a particular construction which is efficient. Okay. So this very formal context can be explained in the case of the homographic collection. So here, our group gamma is a subgroup of SL2. Okay. R is a C algebra functions in one complex variable, Z, with some assumption. The first one is that R must be stable by the complex derivative dz, which is, of course, the derivation which will be present in the problem. R must be stable under the homographic action of gamma. That means that if gamma is an element of the group gamma, the action on F, which is defined by the homography, must stabilize R, the algebra R, and then the function S gamma, which maps Z to CZ plus D, must be invertible in R. These assumptions are not so restrictive. There are a lot of examples where they are satisfied. And of course, the fundamental remark is that this particular S is a one cosical. This is very easy to observe. And if we compute by classical student formula the derivative of f az plus b over cz plus d, we obtain precisely f prime calculated az plus b over cz plus d multiplied by 1 over cz plus d squared. That means precisely the condition, which is a compatibility condition of our general frame. So we can apply directly for, in this case, the previous construction. We have the compatibility construction. So with the previous data and assumption, we can construct, we can extend the action to B and to C. The action of C on R extends to an action by automorphism on the quadratic pseudodifferential operators by setting this relation. That means the action of gamma on the variable y is series, Laurent series with combinatorial coefficient, of course, very, very combinatorial coefficient on the powers of odd powers of y. And this formula one implies by iteration, I recall that x is y squared. So this formula implies directly that the action of gamma on I squared, which is x, is given by this relation, which gives the extension of the action of gamma to the algebra of pseudodifferential operator B. So the situation is known in this case. And we now apply our general criterion to have to describe the sub-algebra of invariants. We assume that there exists in R a modular from G2 of a weight 2 invertible in R. Then this element X prime is invariant. The derivation D prime, which is G2 minus 1 D, stabilize the algebra of invariant. And we have our goal, which is to describe the invariant operators B gamma as pseudodifferential operators with coefficient in R gamma. If instead of G2, which is a modular form of weight 2, we have a modular form of weight 1, which is invertible. The square, the square of a modular form of weight 1 is a modular form of weight 2. Then we can apply what is the point 1, and we obtain on the same this relation. So this is there is a lot of notation, there is a lot of situation, but we can summarize the frame on the following way. Here we have a central object, which is the algebra of pseudodifferential operators. By the technical construction, we can embed, we can embed B in a more complicated algebra of Laurent series with all the quadratic differential operators. Thank you. The relation is simple. Here, X is just the square of. The action of gamma satisfies the compatibility condition to consider in B the algebra of invariant operator B gamma, which can be described as differential operators in one variable X prime with coefficient R gamma, and the same for C gamma. And of course, the extension B is an extension of B gamma, C is the extension of C gamma, and we have this with this square, and the change of notation and convention are explained here. Other other problem, but I will not give detail about it. That's the polynomial subalgebra also works in this schema. So this is the general framework. Now we can give much more details on this homographic collection, studying the arithmetical application. And this is my François, which is explained the second part of the paper.
Hi. So now François has explained all the framework, the algebraic framework, and the goal of this third part is to show some application to modular forms from arithmetical point of view and what we can obtain from the algebraic context to arithmetical modular forms. So at first, we have the framework that François has described. So we have the algebra B of pseudodifferential operators in the variable x, included in the algebra C, which is the quadratic extension, which in arithmetical point of view will allow for us arithmeticians to include the odd weight modular forms, which are very interesting objects in arithmetical point of view. And with B, we have only the even weight modular form, which is very interesting. But to include the odd weight modular forms is a step that we are very happy to do to have a non-commutative product on this basis. So we have the framework here, and we are going to denote Cm, the subspace of element of C whose valuation in Y is greater or equal to M. So they are the series which begins on M. So we can write there as a summation of Fj y to the j for j greater or equal to M. And it is natural to consider the projection Pm from Cm to R, which gives the coefficient on y to the m, so Fm. It is a projection to the main coefficient. As we could see this as the main coefficient. Cm is a subspace. We can also consider Bm, the same construction in B, but for the x valuation, and x being equal to y square, Bm is included in C2m, because x to the y is equal to y to the 2i. So we have this construction. And the first proposition is not too difficult to show. It is that if we restrict Pm to the invariant elements of Cm, we have an additive map which is whose image is included in the space of modular forms of weight M. So Mm here is the subspace of modular forms of weight M in R. So as I recall here, it is the element of satisfying the modularity condition of weight M. So we have this. It is natural because if you take an element U in Cm, so we can write this element of this way. We can show that the action of an element gamma it is complicated, it is twisted, but it begins always by the action of gamma to Fm, y to the m plus element. So it is, when we see that, we understand that when we have an invariant pseudo-differential operators, it gives rise to a modular form from coefficients in y to the m. Okay, donc we have this projection, and a natural question then. Oh, it is. We have the question: can we, with this construction, can we build some linear morphism psi m who could give rise to some right inverse to Pm? So the objective is that we have this formula here. Pi m circle psi m equal identity on the subspace mm of modular forms of weight m. How to do this? We have possibilities to, so the goal is to take modular forms of weight m and build an operator, a pseudo-differential operator in C, such that the first coefficient is f y to the m plus some element. To build some morphism, it is not equivalent, but we have searched to have equivariant splitting map. So the first condition that we would like to have is that an equivariancy from the action of gamma. What I mean by this, it is, can we find psi m such that for any f in R, the image by psi m of f slash m gamma is equal to the action of gamma on the image psi m f on f. So it is equivariant condition, and if we have this for any f on R for any gamma in gamma, naturally we have what we wanted. It is, if f is a modular forms of weight m, so f slash m gamma is equal to f for any gamma, then psi m f is an invariant pseudo-differential operator. So we would like to have this condition C1, and then for arithmetical purposes, we would like to have an expression of psi m f, which is some linear combination of derivatives of f. So what I mean, it is, can we express psi mf as a summation on n, so n a coefficient, a complex coefficient alpha mn, the derivative of f to the n derivative of f, so dn of f, and y to the m plus 2n, because morally, if you derivate f, you have a step of 2 for the valuation in y. So it is the objective. And to have the condition of Pm circle Cm is equal to identity, we would like that the coefficient for y to the m is equal to 1. It is, we would like that Cm f is f y to the m plus some coefficient. We want that if we take the projection of pi m of psi m f, it gives f. So that is not our goal. Is it possible to build some linear morphism satisfying the three conditions? If we have that, then we are going to give an isomorphism between the space of modular forms, the space of sequences of modular forms, and the algebra of pseudo-differential operators, and it will give some non-commutative structure. What are the results that we have shown in this paper? There are three cases. In non-negative case, for M non-negative, we have existence and unicity of a map psi M satisfying all conditions. This is the perfect case. We have a map and it is unique. We have no problem to have there is a unique map satisfying the three conditions. So this result was known by Cohen, Manin, and Zaghir, but only in the even case. So here we have the result even for even and odd non-negative integer. If M is negative, then we have two cases. If M is even, we have existence of a map satisfying the three conditions, but we do not have unicity. We have many maps, but there is a canonical one that we prefer. I will express because there is a unique one which is polynomial in the variable y. So if M is even, negative and even, we can construct this map to give a splitting map on R. But if M is negative and odd, then there exists no map. We cannot construct a map satisfying the three conditions C1, C2, and C3. So there is an obstruction that I will present after if M is negative and odd. And I gave the formula here. We have found during our calculation, we have made the calculation for the different cases, and we have found at the end that we have a unified formula which is valid for any case where we can construct psi M. So this is the formula unified for any cases where we can construct some psi M. Maybe I can fast explain what the problem in the negative case. In the negative case, in arithmetic, we have an identity which is known as Boll's identity, which proves, in fact, that if you have a modular forms of weight minus n, then take the derivative of f, the n+1 derivative of f, it gives rise to a modular forms of weight n+2. So what is this identity? This is this one. It is an identity of the action of gamma. If you take the derivative n+1 derivative of the action of weight minus n of gamma to f, you have exactly the action of gamma of weight n+2 on the n+1 derivative of f. And naturally, if f is a modular form, it gives this condition, which is the condition that we are going to have. Why is this identity an explanation on the result, the previous result? In the even negative M, for even negative M, so I will write M equal to -2k, where k is a positive integer. We can have a map. We can build a map psi M, so psi -2k, which gives a splitting map to R, which satisfies conditions C1, C2, and C3. This is this one. It begins by f x to the minus k, and it is after we have some coefficients. Here we can show that it stops to negative powers of x, but we can also add for any complex c this expression. So the map that we have built in non-negative case applied to the derivative of f, the 2k plus 1 derivative of f, which is, by the Ball's identity, a modular form of weight 2k plus 2. So we can add some coefficients and powers of x, because here we have even integers, in many powers of x. So this is why we have not a unicity of the splitting map. And for odd m, we can show that it is impossible to have a polynomial expression of psi m which satisfies conditions C1 and C2. In fact, the only maps satisfying C1 and C2 for m equal to minus 2k plus 1 are the map only here that we built here, but in the odd case, it begins here, psi minus 2k plus cat. It is equal to, when we begin this by c, and the derivative of f of order 2k, y to the 2k plus 1, and we have no coefficient in minus 2k plus 1. So it doesn't satisfy C3, and we cannot have a right inverse of the projection map. This is why we have a particular case on negative for negative integers here. And what I have what we have as a corollary of these constructions, and it is a theorem that Cohen, Manin, and Zagier had shown for even weights, even non-negative weights, is the following. Now, for we can extend, and in the paper we explain how to extend, but to be not too technical, I take only the non-negative weights. Take the B0 and C0, the element of B and C of non-negative valuation in X or in Y, it is the same. And we are going to consider the algebra M0, which is the sequences of modular forms. It is the set of sequences of modular forms of any non-negative weight. So we can write that as the product on J non-negative of the modular forms Mj. And we can also consider the even description of this, only the product of the even space, of the space of even weight modular forms. Okay, by the transport of structure that, by the theorem that we have shown earlier, we can now construct a vector space isomorphism. So it is what François has described in the beginning of the speech. We can construct big psi from M0 to C, to the invariant of C0, defined by the summation. If you take sequences f tilde, which is f0, f1, f2, sequences of modular forms of any non-negative weight, you can apply and construct the operator, the pseudodifferential operator, psi of f tilde, which is the summation on M of psi M of fm. And it is because we have the construction of psi m earlier. It is a vector space isomorphism between M0 and the invariant of C0, the element of C0, which are invariant by the action of gamma. So, as C0 gamma is a non-commutative algebra, by transport of structure, we give to M0 a structure of a non-commutative product. It is an associative C algebra, but provided with a non-commutative product. And in number theory, the modular forms are very commutative elements. It is a function, so we have and it is really interesting to give a non-commutative structure on the spaces of modular forms which are naturally commutative. How is defined the non-commutative product? But it is really simple. You take two sequences of modular forms, f-tilde and j-tilde, and you transport it by psi to the ring of pseudodifferential operators. You multiply, it is non-commutative, and then thereafter, because psi is an isomorphism, you apply the inverse of psi, and you give rise to a sequence of modular forms given by this operation. And the restriction of psi to the subspace of modular forms of even weight determines also a vector space isomorphism between the modular forms of even weight, the sequences of modular forms of even weight, and B0 gamma. It is what was studied by Cohen, Manin, and Zaghir, and we have so extended to odd weight too. It is the end, but I can just explain maybe why I gave condition C2, which are why I wanted to have a psi m which was linear on the derivative of f. It is because if you take the special sequences constituted of only one modular forms and the rest of the terms are zero. So you take f weight k modular forms, g weight L modular form, and you consider the sequences given by f and the sequences given by g, where all the other coefficients are zero. And then you can give a product of f and g by the previous construction. And the fact that psi k and psi L are derivatives is given by linear combination of derivatives of f assure us that the result f star g here is necessarily given as a combination of brackets here, and so it is the summation of n of a coefficient alpha n k L. It can be very complicated, technical, but multiplied by the nm Rankine-Cohen bracket of f and g. It is defined by this formula, and it is known in arithmetic because it is the only bilinear combination of derivative of f and j which give rise to a modular forms. When you derivative a modular forms, you don't have modular forms. It is not stable by derivative, but you can do some combination of derivative of f and g, bilinear combination, which gives rise to modular forms, and the only one up to constant is given by the Rankine-Cohen bracket. So this is why we have the certitude that f star g is given by this formula, because we have only modular forms which will appear, and they are built as a combination of bilinear derivative of f and derivative of g. we have done some computations, technical computations. So I gave some example here. I will not, maybe it is the time to stop this speech because it is really technical, but we have some computation here which express exactly the space, this isomorphism psi 0. And I'm really speed. We can so you see this is a technical, really technical, but we have an expression, and thereafter the expression here can be used to have calculation on modular forms given by what François has expressed earlier. It is that the invariant of B or the invariant on C, B gamma, C gamma, are in fact pseudo-differential operator on a variable X prime or Y prime, and you can give some technical calculation to have some result on modular forms by this construction. Okay, I think we are going to stop here, and thank you very much for your attention. And we are
Thank you.
here.
Thank you very much. Are there any questions? Comments?
Yeah, now I see why we gave the prize to them.
Yeah, very nice. I like it very much.
Yeah, congratulations.
So, I have a stupid question, probably. This kind of representation is true, have the possibility to have this kind of representation with the parameter is not a natural number, it's a real number.
So it is really interesting, yes, in arithmetics, we can have modular forms of weight non-integer, but rational weight or even real weight. It is much complicated to have some arithmetical content because it is very object of both algebraic and analytic nature, which is and it is complicated to give some weights which are not integer. We have Zagir, which is very known for his study in modular forms, as studied modular forms of half integer weights, and it is really interesting. Maybe we could, but have a quadratical extension of C, which give rise to the modular forms of half integer weight, but it was really technical, the calculation, and we are not sure that we can do some quadratical expression which give rise to formulas which are expressive.
Yes.
Thanks.
Is there any other question or comment? Okay, so let's thank the winners again.
Thank you very much.